All right, ladies and gentlemen, boys and girls, this is your video lesson for the day. We are talking about solving systems of linear equations by graphing in your online textbook. This is lesson 11.1. The good news about this lesson is that you know about 90% of everything you need to know for this lesson because you know how to graph lines. All we're looking for today is the solution for a system. And, well, what is a system to begin with? Okay? So the good news is, like I said, we already know 90% of it. What we're trying to do is figure out what a system of equations is and what a system's solution has to do with graphing. Okay, so let's look at this warm-up problem. We're going to start with this, and then we're going to double back and solve this at the end. Okay? So I want you to think about how you might solve this using any method that you would know right now. And then at the end, we'll use today's technique to solve it. All right, so how can we find a solution to this problem? Cora ran 3 miles last week and will run 7 miles per week from now on. Hannah ran 9 miles last week and will run 4 miles per week after that. After how many weeks will Cora and Hannah have run the same number of miles, and how many miles will that be? Well, let's separate both people's situation. Let's look at Cora's situation and let's look at Hannah's situation. And maybe we can write an equation for each one. All right, so Cora ran 3 miles last week and will run 7 miles per week from now on. So she's already run 3 miles, and she's adding to that by 7 miles per week. So we can call X that week amount, so we can define X as weeks. And we can set all of that equal to a variable. And if we look at 3 miles total plus 7 miles per week, y would then be equal to the total miles. Okay, so if we did the same thing for Hannah, Hannah ran 9 miles last week, and we could start off the same way. Y is equal to, she's already had 9 miles, so y is equal to 9. And she's adding to that, she will run 4 miles per week herself, so plus 4x. All right, so those are the two equations that we got for that. When we're asked the question, Hannah, okay, so we want to know how many weeks Cora and Hannah will have to run until they get the same number of miles. So we want to know when x is the same, and we want to know how many miles that will be. So when will the y's be the same? So I want you to think about ways you might want to solve that. And we are going to move on to learning the technique that we'll double back to later. All right, so first of all, let's talk about this. I know this is already spelled out for you on your sheet, but let's talk about what a system of equations is. A system of equations is 2 or more linear equations that have the same variables. So they have to have the same variables, and those 2 variables will be x and y usually, but it can be t and w. It doesn't make a difference. But more importantly, those variables have to have the same meaning. So if we look back at this problem, both of these equations had x and y, right? And they meant the same thing. All right, so if you have 2 or more equations that have the same variables, and those variables mean the same thing, that is a system of equations. All right, well, what is the solution? How do I know I have a solution to a system of equations? So a solution is an ordered pair. Remember, an ordered pair is an xy coordinate that we can graph, and that satisfies both equations in the system. The ordered pair, really this is what we're looking at today, where the 2 lines intersect. So when we were writing these 2 equations before, we wrote these in y equals mx plus b form, right? And so you should have thought it right away, well, we could probably graph these. Okay, well, right now we're looking at the solution being, this keeps going away on me, the solution being where the 2 lines intersect, right? So that's how we are going to tackle this today. We're going to graph both lines and see where the lines intersect. That will be our solution. All right, so first a little bit of background here. First, the first way we identify a solution. So we said that it's an ordered pair that satisfies both equations in the system. If we look at this, I have 2 equations that have both the same variables, right? So they are a system, and we want to know if this is a solution. We want to know if it satisfies both equations. What that means is that can I plug this in x and y in for x and y and get true results at the end. So let's try out both of these, all right? So I have to substitute both x and y into this equation and then into that one. So let's take a look. In the top equation, my y value is going to be 6, and that will then be equal to 3 times, and now my x value is, oops, my bad, switch that up. My y value, sorry about that, is 11. So I'll start over. Y is 11 is equal to 3 times my x value, which is 6, minus 7. And now I just have to see if this is true. I get 11 is equal to 3 times 6 is 18. And then 11 is equal to 18 minus 7 is 11. All right, so far so good. What that means is that this point is on that line. I'm trying to see if it's also a point on that line. If we find that, then we found the point of intersection. We share that point in common. All right, so 2 times y, which is 11, minus 2 times x, which is 6, it must be equal to 10. All right, 2 times 11 is 22, minus 2 times 6, which is 12, is equals 10. 22 minus 12 is 10, and I get 10 is equal to 10. And so it checks out. So I can say that 6 comma 11 is a solution. I'll abbreviate that SOL. Okay. Well, we want to check also to see if there are other solutions. All right. So let's check and see if 1, negative 4 is a solution. I have to go back up here and write both these equations down. So y is equal to 3x minus 7, and the other one is 2y minus 2x equals 10. All right, now, give myself some workspace here. It's the same exact process. I'm going to substitute in my negative 4 in for y is equal to 3 times x is 1 minus 7. Okay, so I get negative 4 is equal to 3 times 1 is 3 minus 7. And so far it looks like 3 minus 7 is negative 4, so this point is actually on that same line up there. So far it's looking like we might have 2 solutions for this. Let's see if it works out for the other one. It's 2 times negative 4 for y, minus 2 times 1 for x is equal to 10. 2 times negative 4 is negative 8, minus 2 times 1, which is 2, is equal to 10, and I get negative 10 is equal to 10. So actually, that's not true. So we would say no, not, bring it up a little bit, not a solution. Because it only lies on one line, we've verified that algebraically, and it does not lie on the other line. So go back to this. This is the solution, that is not. Okay, so let's take a look at, so that's verifying if it's a solution algebraically. That's going to be some of the first questions you have on your worksheet tonight. So make sure that if you need to, you can go back and watch this video, but make sure you pay attention to that part again when you watch it later. All right, solving systems by graphing. This is the method that we're focusing on today. So this is very straightforward. To solve systems of equations by graphing, we must graph each line. The point of intersection is a solution. Remember, you need to report out what that is. You can't just graph both lines and then leave it like that. You have to tell me that that's the intersection point. So let's look at the first one. This is nice because it's in slope-intercept form, right? So my y-intercept is 2. So I'll put a point at 2. My slope is 2, and I can put that over 1 if I like, which means I go up 2, right 1, up 2, right 1, up 2, right 1. When you're doing this by graphing, it is very helpful to put points all the way across the graph, because what you'll end up doing is actually putting your pencil directly on the solution. So put all the points all the way across. And this one I can do one of 2 ways. I can use the intercept method, or I can solve for y. I'm just going to solve for y because that's pretty simple in this one. If I subtract x from both sides, I will get y is equal to negative x plus 5. I will do this line in blue, and my y-intercept is 5, so I'm up at 2, 3, 4, 5. And my slope is negative 1. Remember, that's that, so I go down 1 and then right 1. So down 1, right 1. Look, I already put my pencil right on the solution. Put some more points on there. There's my line. A little bit off here. And that's where they intersect. So what is the solution to my system of equations? That is the point 1, 2, 1, 2, 3, 4. So I have point 1, comma 4. You will have to identify that and write it out just like I did. And that is the point that is on both lines. Okay, so that is our system of equations solving by graphing. Like I said, you already knew 90% of this today because you knew how to graph lines. Now we're just adding some vocabulary. But what if I wanted to verify that algebraically? Okay? So again, going back to these two equations here, if I want to verify the solution algebraically, I would have to know if, if I plug in the x and y values in for each x and y in each equation, do I get true statements, right? So if you don't have this on your sheet, I'm just showing you. So this is the first equation, y is equal to 2 plus 2x. I'm substituting in those values. So I kind of scribbled over the top, but that 4 goes in for y, and that 1 goes in for, so it's here, I'm doing it real time here, is there, right? And the 4 is in for y. So on the right-hand side, I get 4 is equal to 2 plus 2. I get 4 equals 4, checks out. And then I have to try the other equation. I'd have to plug it in here. Well, that we can do mentally, right? This is x, that's y. If I substitute both in, let's get rid of the shade. If I substitute both in, I end up with basically 1 plus 4 equals 5, and 5 equals 5, so it works out. So we can verify algebraically, and we can verify on the graph. You will be asked to do both on your independent practice. Okay, let's go through a couple more examples here. Two equations, they share the same variables. They are a system. We are going to graph them and see where they intersect. All right, so first one's got a y-intercept of 4, so I'm up at 4 here. And my slope is -3, so I go down 1, 2, 3, right 1. 1, 2, 3, right 1. And I can go all the way down to the graph. And there's that line. Do this one in green. I have a y-intercept of -2. And I have a slope of +3. So up 1, 2, 3, right 1. And look, I put my pencil right on the solution. 1, 2, 3, right 1. And that's where the two lines intersect. And what is that point? I got to report it out. That's the point 1, comma 1. Again, if we plug both of those values, x, comma y, into each equation, we get true statements. All right. Well, both of these are not in slope-intercept form. Is that a big deal? I don't think so, because we can just solve for y. Remember, if you solve for y, if you solve a linear equation for y, you will get y equals mx plus b. So the first one, I'll just rewrite it, 4x plus y is equal to 2. And all I have to do is subtract that 4x this time. So I'll end up y is equal to -4x plus 2. All right, so the y-intercept is 2. My slope is -4, so I go down 1, 2, 3, 4, right 1. And those are actually the only 2 points I can put on the line. So I'll carefully graph this. And I will also have to solve for y in the next one. So I'm going to get rid of this work for a second. I didn't mention this earlier, but if you need to pause the video at any time, please do. I'm going faster, obviously, than I would in normal class because, well, no one's here to ask questions. So go ahead and pause this video at any time to help you out. So go ahead and take this one. X minus y is equal to 3. I'm going to subtract that x minus x. So I'll end up with -y is equal to -x plus 3. Remember, I cannot end up with a negative variable if I'm trying to solve for it. I got to get rid of it, so I'm going to divide by that -1. And I end up with y is equal to negative divided by negative is positive, x minus 3. All right, so we're going to -3 on the y-axis, and I go up 1, right 1, and again, I put my pencil right on the solution. So there's my line. There we go. So what is the solution for that system of equations? 1 comma -2. That is the point of intersection. Awesome. Okay, so here's what I would like you to do. I would like the video to be paused right now, and I would like you to work on these on your own just for a couple minutes, okay? You will get interesting scenarios, and I want you to try to answer these questions. Maybe not write anything down, but in your groups discuss, like, well, what do you think this means? Okay, you're going to notice something interesting. So go ahead and pause the video and go ahead and try to graph them. All right? When you come back, I will have these somewhat graphed myself. Okay? Go ahead. Okay, so at this point, I have already graphed the top line here in blue, and you can see it on the graph. The y-intercept is 2, and I've gone down to right 1 to get my points. Okay? The second equation, you had to solve for y. And when you solve for y, you end up with this equation. Is there anything similar between these two equations? They're exactly the same. So if you were to try to graph them, you would literally graph a line right on top of the other line. Well, let's think about this. What does that mean about the solution? If we go back to the beginning of the lesson, we said that a solution to a system of equations is where those two lines intersect. Well, what would we say here? The question kind of becomes like, well, how many times do they intersect? Clearly they intersect more than one time, and the answer to that is infinitely many solutions. So when you have two equations that don't appear to be the same, but then you graph them and they end up being the exact same line, we can say that we have infinitely many solutions. I usually abbreviate that like infinitely many solutions. So I would be okay if you guys did that as well. Okay? Neither. Okay. So if you haven't done the other one, go ahead and do that. I'm going to graph it and then come back and you guys will see. Okay, so I've already graphed the blue line and it had a y-intercept of 5 and a slope of 1/2. So oh darn it, hold on a second. Did you guys see how fast I changed that line? Whew, awesome. Okay, now it has a slope of 1/2. Before I accidentally graphed negative 1/2. Anyways, so we had a y-intercept of 5, slope of 1/2, couldn't go up 1, right 2, so I had to go down 1, left 2, use it exactly backwards. All right, I had to take the second equation and solve it for y. When I did that, I ended up with this line. Okay, y is equal to 1/2 x plus 8. Notice they have the same slope, but the y-intercepts are different. Right? So what does that actually get 4 here? Not 8. So my y-intercept is 4, and I go up 1, right 2, and I can't go any further, so I have to go the other way. Down 1, left 2, down 1, left 2, and now we have to think about what the solutions are for this. So let's think about this for a second. Okay, so again, the solution to a system of equations is where the two lines intersect. If we think about where these may intersect, where would that be? Well, they both start at different spots. And to get to the next point, they use the exact same rise over run directions. They have the same slope. So will they actually ever intersect? Nope, they will not. So what do we say here? What we say is that there is no solution. Okay, so we can add that down here. So when we have, let's go back up to the top, when we have lines that have the same slope, right, but different y-intercepts, then those lines have no solution. So again, let's read this all together. What conclusions can we draw about the types of solutions of system equations given the problems we have done so far? So these two examples gave us examples of infinitely many solutions if they're same exact line, no solutions if they have the same slope and different y-intercept, but the last solution we can actually get is an x comma y coordinate point if they actually intersect. So there are 3 types, right? 3 types of solutions. Okay, so let's double back to that problem we talked about before. How can we find the solution to the problem that we had? So let's read it one more time. Cora ran 3 miles last week and will run 7 miles per week from now on. And we wrote an equation for that. We had y is equal to 3 that she'd already ran, right? This is Cora. And she's adding 7 per week. Okay? And then Hannah, what's her situation? Hannah ran 9 miles last week, so we said, well, that was y is equal to 9. And she's adding to that 4 miles per week. All right, so Cora started with less, but is gaining more, and Hannah started with more, but is gaining less. So this leads me to believe, if we think about what these lines would look like, it leads me to believe that they will intersect. Okay, so again, let's just define our variables one more time so we have that done. X, remember, is the amount of weeks, and Y is total miles. I have already pre-numbered my graph here. Notice I'm counting by 0.5s on the X, and I'm counting by 1s on the Y. That's okay. It just made it easier to see what's happening with these lines. Okay, so Cora's line, I'll do that one in green. Y is equal to 3 plus 7x, so I have a y-intercept of 3, which is right here. and I'm going up 7 and right 1. In fact, in this scale, it's actually right 2. So up 1, 2, 3, 4, 5, 6, 7. That's my next point. 1, 2, 3, 4, 5, 6, 7. That's my next point. So this is the line that would show Cora's progress of running and accumulating miles. I will do this line here for Hannah in blue. She has a y-intercept of 9. And her slope is 4. 1, 2, 3, 4, right 1. 1, 2, 3, 4, right 1. And I have found my solution. Graph the line quickly. And so, what do we have? That is the point 2, 17. All right, so what does that mean? Did we answer the question? It says after how many weeks will Cora and Hannah have run the same number of miles, and how many miles will that be? Well, my x value, my x-axis, represents time in weeks. So we can say in 2 weeks, and then we come across what the y information tells us. In 2 weeks, they will run, distance is y, that's my y value, 17 miles. In 2 weeks, they will both run 17 miles. Awesome. Okay, so what we talked about today was solving systems of equations by graphing. 3 key parts here. There are 3 things that can happen. Remember, we can get lines to intersect, and we get a singular solution. You always have to report out what the x, y coordinate point is, where they cross. And we can get infinitely many solutions when they are the same line, or no solution when they are the same slope but different y-intercepts. And then we can apply this to real-world situations just like we have in the past. Big key here for understanding the interpretation is knowing what x and y represent, which comes from the very beginning after you write your equation. All right, so you guys have a worksheet tonight, solving systems of equations by graphing. The substitute teacher will now hand that out to you, and you should have a decent amount of time to get this thing knocked out. I will talk to you guys when I get back from San Antonio. Peace.